Welcome back, students, for our second part of the coordination chemistry. So now, in the last class, we have seen the definition of molecular compounds and what are the coordinate complex compounds and how that coordinate covalent bonds are forming, and some terms of coordination chemistry like complex ion, ligand, central metal ion. These all things we have seen in the last class. So in today's class, we will see the types of ligands based on what they are classified. So as we have known in the last class that ligand is capable of donating one or more lone pair of electrons to the central metal atom, forming a coordinate bond, and the atom through which the ligand is bond to the central atom is called a donor atom or a donor site. So depending upon the presence of the donor sites, the following ligands are classified as monodentate, bidentate, tridentate, tetradentate, hexadentate, and polydentate. So first we will see the monodentate ligand. So monodentate means it has only one donor site through which it can donate with the central metal atom. So example we will see that is water molecule. So here in this case oxygen is an electronegative atom and it has a lone pair of electron through which it can donate with the metal atom. So next example we will see that is a cyanide molecule. So cyanide basically is an ambidentate ligand. Why this one is an ambidentate? Because it can donate with the metal atom through carbon also and through nitrogen also. If it is, in this case, if carbon is a donor site, then it is a cyanide. If the nitrogen is a donor site, then it is a isocyanide. So next we'll move towards the biodentate ligand. So in this case we have two donor sites. So example are oxalate ion, ethylene diamine. So this one is abbreviated as a ene. And next third one is orthophenanthroline. So now we'll see the structures of oxalate ion. So that star mark indicates the donor atoms or donor sites through which it can bind with the metal atom. So this is how they will bind with the metal atom. So they will donate their electrons to the metal atom. So in this case ethylene diamine also, nitrogen has a lone, two nitrogens are present. Both the nitrogen have a lone pair of electrons and both the nitrogen will donate their lone pair of electron to the central metal atom. Next orthophenanthroline also, same, the nitrogens are present and those nitrogen will donate their lone pair of electron to the central metal atom. So next we'll see the hexadentate ligand. Hexa, or else we can say it has a polydentate ligand. So more than two donor sites, those will call it as a polydentate ligand. So example is ethylene diamine tetraacetate. So in this case we have 6 donor sites through which they will bind with the metal atom. So in this way they will bind with the central metal atom. So in this case ethylene diamine tetraacetate, totally 4 oxygens are the donor sites and 2 nitrogens are the donor sites through which they will donate their electrons to the central atom, metal atom. So next we'll see how to calculate the charge present on the central metal atom. So here we'll take the example of tetraamino copper. So in this case we are going to calculate the charge present on the copper molecule or central metal. For that reason we'll put it as a X, and total number of ammonia are 4. So the charge present on the ammonia is 0. Hence X is equals to plus 2. And the charge present on the copper is plus 2. So next we'll see the Werner theory. So Werner possesses two types of valencies. One is primary valency and the second is secondary valency. So primary valency refers to the oxidation state. So whatever in the last slide we have calculated, so that is what the oxidation state. And the secondary valency, we will call it as a coordination number. The number of ligands present in the complex ion, so those are the coordination numbers. Primary valencies are satisfied by the negative ion and secondary valency may be satisfied by the negative or the neutral molecules. And the third point is ligands satisfying secondary valencies are directed towards the fixed position in a space, giving a definite geometry to the complex. So now through the example we can see how that secondary valencies have definite geometry. Example we will see, that is tetra amino copper. So here copper is a central metal atom. Hexamino copper. So in this case total number of amines are ammonia are 6, through which so now this one is forming an octahedral structure. So this is what they will give a correct geometry to the complex. So thank you. In the next slide, next class we will see that in the next class we will see about the IUPAC nomenclature of coordination compounds. Thank you.